2 hours early. 951, flip equivalent binary trees. For a binary tree T, we can define a flip operation as follows. Choose any node and swap the left and right child subtrees. A binary tree X is flip equivalent to a binary tree Y if and only if we can make it X equal to Y after some number of flip operations. Given the roots of two binary trees, root 1 and root 2, return true if the trees are flip equivalent or false otherwise. Well, let's see. So how would this not just be check if all the levels are the same? I think it's because you could have a 6 over on this side. Let's see. What are the topics here? The first search binary tree. Well, what if we so it's not if the levels are the same, but rather if the sequences are the same. So the first solution idea, not necessarily brute force, first solution idea. We can, the first solution would be to so you can't just my first thought would be, okay, can you see if just all the levels are equal? So like the first level has a 2 and a 3, so does this one have a 2 and a 3? Because then you can just flip them if they're out of order. But that's not the case. What if we basically put them? So my first solution idea, I have another. Okay, two solution ideas, and we're gonna work with them. So my first solution idea is that you just follow all paths from root to leaf, and then check if those paths are in both. So for example, this one has 1, 2, 5, 7, and this one has 1, 2, 5, 7. So if they have all the same paths, then it should work. Except, would it? Yeah, that would work. But it would be pretty space intensive because you would require you would require one array for every single path, which would be like n arrays, where n is the number of nodes. So that's too many. So that'd be kind of like a trie, T-R-I-E. I'm thinking the second solution, which is just turn it into not a binary search tree, but just basically force it into order. I don't know actually what tree that would be. It's not a binary search tree, because a binary search tree, they would all be, like, all the values to the left would be less. But this doesn't have any rules. So I'm thinking that basically you force it to be the same. And what I mean by that is we could just say have the left be the lower value than the right. Are they unique values? Are they unique values? Unique. Yep, unique node values. So that's huge. Have the left be the lower value than the right, and then just compare the nodes at the end. So I think that's it. So how do we do that? This is definitely better than this. In fact, I'm going to delete this because this is just too space intensive. I think that it would work, but it would just take way too long. So we're going to say force it to be the same. Have the left be the lower value than the right. How? Recurse through the tree. We'll default to the left if there's only one value, but we'll say if there's two values, then we could just say node left right equals right left. Yeah. And if there's one value, put it on the left. If there's no values, stop recursion. Finally, we can just compare the two nodes. I think that we can literally just compare root 1 to root 2. I think that should work, especially in Python, which equality seems to be pretty helpful, pretty easy. Let's do this. So, we'll say define force pattern. And this is going to take in just a node, optional tree node, because it could be nothing. No, well, it won't be nothing, but it could be. And this is just going to return nothing because it's actually altering the nodes in place. Okay, so first we say if not node, return. Otherwise, we say if node left and node right. So if there are two children, then say, actually we can say if node left and node right, we'll say if node left val is greater than, they'll never be equal, so don't have to worry about equals, but because they'll be unique values, so that'll make it easier for us. If node left.val is greater than or equal to node right.val, then just swap them. So node left, node right equals node right, node left. Don't you just love Python? Yeah. Then we had to deal with the condition. Oh yeah. Then we had to deal with the condition. Okay, then we'll recurse from there. We'll say force pattern on the left subtree and the right subtree. Node left and node right. Now we'll say elif node right. Then we'll say node left equals node right, and node right equals none. I'm worried about the pointers. Sometimes the pointers in this are weird. Like you think that you're just taking one thing, but actually you're affecting, like, you know, when we say node right equals none, we're worried that this is going to turn node left into none. But we'll see. And then recurse on node left. Otherwise, if that means that it's node left, so we can just say else force pattern on node left. So let's see. So we say force pattern on node left every single time. So we could just say that all at the end. What if we just say force pattern node left at the very end, since we already say that 3 times? Because no matter what, we're forcing the pattern on node left. Okay. So if there's both, then we force the pattern on node right, and we swap the left and right nodes. If we get to this point, then that means that they're not both true, and only node right is true. No. And we check if only a node right is true. If node right is true, then we set node left equal to node right. We could do this in one line. We could say node left, node right equals node right and none. I guess we could just even do node left, but I'm not worried about that. And then we just force the pattern on node left because we swap the right over the left. And this one we swap the right over the left. And on this one and if we get to the end, if neither of these are true, then that means that only node left is true. We'll just also put in a condition that checks if neither of them are true. We'll say if not, we'll just say return to stop it. That should do it. Because if you get to this point, that means that one of them are true. So you check if both of them are true and you swap them if so. Otherwise, if only one of them are true, being node right, then you swap right to the left. And then you force the pattern on the node left. Okay, so then we would just say force pattern on root 1 and root 2. And then we'll just say return root 1 equals root 2. Well, that's not good. That only worked for those edge cases. All right, let's debug it. Where is this going wrong? So first we have the node, which is 1, 2, 3. So it's 1, 2, 3. So, oh wait, this should actually be or. Let's see if that works. Wrong answer. Okay, debug. So 1, 2, 3. So there is a node. Then we check if one of them is true, which at least one of them is. Node left and node right. Okay. Node left val is not greater than node right val. So now we force the pattern on node right, which should be 3. So node should be 3. If not node. One of them is true. Both of them are not true. Node right should be false. So now we run it on 6. And there's nothing, so we return nothing. Okay, so now we run it on 2. 2 is a node. 2 is, well, it has 2 children. Node left and node right are both true. Node left is greater than node, or is less than node right. So you don't swap them. So you try it on the right tree, which will be 5, 5, 7, 8. If not node, it is a node. It has both children. 7 is less than 8. So you force the pattern on node right. It has no children, so we stop. Try it on 7, it has no children, so we stop. We can also make that just one line. 4 has no children, so we stop. Okay, so now we do it on 3. This is where it should happen. It has 2 children, so we go into this. Node left val is greater than node right val. So we say node left is greater than, well, is equal to node right, and node right is equal to node left. Does that work? It seems like it did. One, two, three, 1, 3, 2. Okay, so then we go on 3. 3 is a node. There is a child. It's not node left and node right. So we check to see if node right is true, which it is. So we say node left equals node right, and node right equals none. So now we do it on 6. Yeah. So 2, 4, 5. It does have children, but they're both, but they're in order. So now we do it on the right. 5, 8, 7. So it should swap them. So let me just say print node. I don't know. Okay, let's see. Okay, so that's going to be too tough to read. Okay, now 1, left is 2, left of that is 4, left of that is none, right is none, right is 5. They are the same, it's just the equals isn't working. So do we just have to make another function to recurse through? Define compare trees, node 1 and do we have to do that? Compare the trees. So we'll have node 1 and node 2. So we'll say if node 1 if not node 1 and not node 2, then return true. If otherwise, if node 1, how do we do XOR? Let's see. Let's say if not node 1 or node 2. So if neither of them are true, return false. Otherwise, return node 1 val equals node 2 val, and compare trees on node 1 left and compare trees on node 1 right. That should do it. And then we just say return compare trees on route 1 to route 2. Returns a bool. Does that work? Oh yeah, sorry, node 1 left, node 2 left, and node 1 right, node 2 right. Does that work? None type object has no oh wait, it should be and. Does that work? All right. I think something's busted with the runtime or something. But yeah, there we go. So there we go. We are forcing them to be the same by applying a rule that the left node must always be less than the right node. If they weren't unique, we'd be in major trouble here, because if you encountered a left and right node that were the same value, you'd have to look at their children. But thankfully, that wasn't a rule, which is why it's a medium and not a hard problem. But yeah, we did it. Happy with that. Thanks for watching. Have a good one.